Hello viewers, welcome back to the course on scientific computing using MATLAB. So, in the previous lectures we have discussed that how we can write the Lagrange interpolation polynomial or Newton divided difference polynomials. So, today we will discuss some example based on this one. So, let us start with the lecture 43. So, let us solve some examples. So, let us take one example. I have some data that is given to me. So, my x coordinates are given to me like 0, 1, 4 and 5, and the value of the function or the y is given to me, that is 8, 11, 68 and 123. So, this is the values is given to me. Now, we want to find Lagrange interpolating polynomial. Interpolating polynomial and approximate y at 2. So, this one I want to approximate. So, 2 will lie here. So, at this value I want to find what is the value of this. Now, in this case I want to use the Lagrange interpolating polynomial. So, you can see that from here the nodal points are not. So, the values of x are given non-uniformly, that the difference between 1 and 0 is 1, then the difference is 3 and then difference is 1. So, this is non-equispaced data that is given to me. Now, we have 4 points of data. So, in this case my polynomial will be cubic because 4 values of the data that is given to me. So, I can write from here the P3x. Now, I can define this should be equal to x minus x1, x minus x4, x minus x5 and then 0 minus 1, 0 minus 4 and 0 minus 5 into the value of the function at x naught. So, this is f0 I am defining plus x minus x0, x minus 4, x minus 5 divided by 1 minus 0, 1 minus 4 and 1 minus 5. So, this is x1. So, this I can write as f at x1 and that is 1 plus x minus 0, x minus 1, x minus 5 divided by, so I am taking now the value corresponding to 4. So, this will be 4 minus 0, 4 minus 1 and 4 minus 5 and the value at 4, and in the end I will get x minus 0, x minus 1, x minus 4 divided by 5 minus 0, 5 minus 1 and 5 minus 4, the value at 5. So, now if I calculate this value, then from here I can see that this is a cubic I am going to get, and this is the values I am going to find out. Now, from here if I do the calculation, so now P3x will be a cubic, and then we have to do the calculation to find out the expression. Now, in this case, if somebody asks me that what is the expression, then we will calculate this all this value, and then we can write this in the form of expression, that is the cubic. Now, we want to find what is the value of P3 at x is equal to 2. So, this one we want to find. So, I will directly put this one here. So, P3 at x is equal to 2 will be what? So, now I can write directly from here. So, this will be 2 minus 1, 2 minus 4, 2 minus 5. So, based on this one values, so this is minus 1, minus 4, minus 5. So, this is minus 20, and F0 is given to me, that is 8 into 8. Okay. And this one also I can calculate. So, it is 2 minus 1, 1, multiply by minus 2, multiply by minus 3. So, it is minus 6. Okay. So, minus 6 by minus 20. So, I can write this expression as minus 6 by minus 20 into 8 plus this one I want to calculate. So, from here I will get 1 minus 3 and minus 4. So, I will get from here 1 into minus 3 into minus 4, and x I am putting 2. So, it will be 2 into minus 2 into minus 3, and F1 is given to me, that is 11 into 11 plus, that is 4 into 3 into minus 1, and it will be 2 into 1, and it is minus 3, and the value of 4 is given, that is 68, plus it is 2 into 1 into minus 2, and this is 5 into 4 into 1, and this is 123. So, if I do all this calculation, the value is coming 18. Okay. So, from here I can see that the value, the interpolating value of P3 at x is equal to 2 is 18. So, here the value is coming 18. So, that is the answer of this question. So, this way we can find the value of the interpolating polynomial at any points given in between the data. So, data is given from 0 to 5, and my 2, the value 2 is in between that one. So, that is why it is called the interpolating polynomial, interpolating equation. Another example I want to do, find the unique polynomial of degree 2 or less for the given data points. So, it is given F0 is 1, F1 is 3, and F3 is 55. So, this value is given to me. Now, let us do this one. So, in this case I want to find the unique polynomial. So, let us see, we already know that whatever the polynomial we are getting using the Lagrange or Newton divided difference, so they are the unique polynomial. So, let us verify this one for this data. So, let us solve this one, the case 1 I am taking using Lagrange. So, I have 3 points that is given to me. So, in this case it is the quadratic. So, points are given to me like this one. Now, I can write the point x and f, at x. So, it is 0, 1 and 3. So, not the spacing is non-equal. Here the spacing is 1, here it is 2. The value is given is 1, 3 and 55. So, 0, 1, 3 and 1, 3, 55. So, that is given to me. Now, I will write from here expression. So, it is x minus 1, x minus 3 divided by 0 minus 1 and 0 minus 3 into 1 plus x minus 0, x minus 3, 1 minus 0 and 1 minus 3 into 3 plus x minus 0, x minus 1, that is 3 minus 0 and 3 minus 1 into 55. So, now from here expression, this expression, now if I multiply this one, so this will be x square and minus 3x and minus x minus 4x plus 3 divided by, this is a minus 1 and minus 3. So, it will be 3 into 1 plus, now it will be x square minus 3x divided by 1 and this is minus 2. So, it will be minus 2 into 3 plus x square minus x divided by 3 into 2, 6 multiplied by 55. So, from here I can write, now based on this one I will collect all the terms corresponding to x2, so x square. So, this expression I can write as 1 by 3 minus 3 by 2 plus 55 by 6 x square. Then I can add all the terms corresponding to x also. So, plus minus 4 by 3 plus 9 by 2 and here minus 55 by 6 into x plus the constant terms. So, it is 3 by 3, no constant term here, no constant term here. So, it is 1. So, now from here this expression, if I do the LCM of this, then I will get 8x square minus 6x plus 1. So, that is my P2x. So, this is the quadratic polynomial we are able to find using these 3 data points. Now, this is we have done with the help of Lagrange. So, let us do this one. Case 2. So, in the case 2 I will use the Newton's divided difference. So, Newton divided difference, now it will be a P2x, it is Fx naught plus x minus x naught, the first divided difference plus x minus x naught, x minus x1 and the second divided difference. So, this one we want to find out. Now, from here I know that f first divided difference, so that is equal to f x1 minus f x naught divided by x1 minus x naught. So, this is, so fx1 is 3 minus 1. So, 3 minus 1 and x1 is 1 and that is 0. So, this is 1 minus 0. So, this is 2 by 1, that is 2. So, this is given to me. Now, I want to find what is x1, x2. So, this is f x 2 minus f x 1 divided by x 2 minus x 1. So, f x 2 is 55. So, it is 55 minus x 1 is 3 divided by 3 minus 1. So, 52 by 2. So, it is 26. So, that is value. Now, I find the second order divided difference. So, this is x 0, x 1, x 2. So, that is equal to first divided difference, the difference of first divided difference divided by x 2 minus x 0. So, f x 1 x 2 is 26, this x 0 x 1 is 2 and x 2 minus x 0. So, x 2 minus x 0 is x 2 is 3 and x 0 is 0. So, it is 3. So, it is 24 by 3 and it is 8. Now, from here my p 2 x become f x naught is given to me, that is already value, that is 1. So, I can write as a 1 plus x minus x naught. So, it is 0 into the expression, that is 2 plus x minus x naught, that is 0, x minus x 1 is 1 and this is the expression into 8. So, from here I can write that this is 1 plus 2x plus, from here I can write this is x square minus x into 8. So, this one I can write. Now, from here I can write that it is 1 plus 2x plus 8x square minus 8x. So, that gives me 8x square minus 6x plus 1. And if you see from here, this is the same expression as we have found using the Lagrange interpolating polynomial. So, from here we can say that the interpolating polynomial is unique. The only thing is that the interpolating polynomial we are calculating using Lagrange interpolation and using the Newton divided differences. So, writing the interpolating polynomial using the Newton divided difference is much easier as compared to the Lagrange interpolating polynomial. So, that is the way we can say, but we have already told that the interpolating polynomial that will be unique. So, it has only two expressions in this form, either it will be of the type Lagrange or the another type it will be Newton divided difference, but this will be unique. So, that is the verification for what we have done in the previous lecture, the theorem about the interpolating polynomial for the non-equispaced data will be unique. So, this is the verification for that one. Now, suppose we want to approximate the value of the function at x is equal to 2. So, let us take at x equal to 2. So, in this case there is no need to rewrite again. I will do that. I will just I know that my p2x is 8x square minus 6x plus 1. So, in this case I will just put the value at x is equal to 2 here. So, it will be 4 minus 6 into 2 plus 1. So, it is 32 minus 12 plus 1. So, it is 21. So, that is the answer of this one. So, the corresponding value at 2 will be 21. So, this will be here somewhere. So, in this case I can say that this function is a increasing function. Now, based on this one, so from here I can find this one. So, based on the data, we can find the maximum error estimate. But the only thing is that I need to know that this is the values represented by some function. So, if I know the value of the function in this case, then I should be able to get the error, that how much error is there. So, f0 is 1, 1 is 3, 3 is 55. So, there if the function is known to us, then only then we are able to find the error estimate of this one. So, this is all about this type of data. Now, the question is that, so we know that in the Lagrange interpolating polynomial there was a two type of drawbacks. One drawback was that, so in the Lagrange interpolating polynomial there was a two drawbacks. One drawback was that we are going to get the higher degree polynomial for a bigger data, and the second one was that if we add one data point, then we have to rewrite the equation again. So, the second drawback has been addressed by this Newton divided difference formula. Now, we will go for the first drawback. So, let us see how to reduce the degree of the interpolating polynomial for large number of data set. So, let us address this issue now. So, in this case what do we do? So, let us take this one. So, suppose I have some data. So, this is, suppose I have some data, this is the some data value x naught y naught, this is x1 y1, this is x2 y2, suppose this is x3 y3, this is xk yk, and in the end I will get xn yn. Now, suppose I want to, so if I find out the interpolating polynomial, the interpolating polynomial will be like this one, like this one. So, this is my interpolating polynomial. Now, but I do not want to apply the interpolating polynomial because the degree will be high. So, what I do in this case, I will do the piecewise approximation. So, in the piecewise approximation what I do, suppose I want to approximate these with a linear interpolation. So, what I do is that I approximate this by this linear function, then this by this linear function, this by this linear function, and this by this linear function, and this is, suppose the previous one is this one. So, this by this linear function, if I take this as x k minus 1, y k minus 1 and so on. So, this type of interpolation is called piecewise interpolation, interpolating polynomial. So, in this case we have the data, and this data we split into the pieces, and then we approximate the pieces based on that which one we want. So, here suppose we have 2 points, then we will approximate with the linear data. Now, what I do is that instead of taking the 1 point, suppose I split the data into 3 points. So, suppose I split the data into 3 points, 3 point this 1, 2, 3, another 3 point are this, like this one. So, what I do that, now I approximate this with a quadratic function like this one. I approximate these 3 points with a quadratic function and so on. And so this is, I call it quadratic interpolating polynomial. So earlier I have done with the piecewise this interpolating polynomial, that is linear function, and now I am doing the same with the quadratic interpolating polynomial, but this is also piecewise. So in this way we are able to approximate the data with a small degree of polynomial, does not matter that how big data is this one. So this type of method, so this is called piecewise approximation. So in this case we will discuss, we will define the piecewise approximation, and for that one in our course we will go for splines. So this is basically we are heading toward the splines, that how we can discuss the splines. So in this case I can write down that for large data we will get higher degree polynomial which implies costly computational. So for this one also computed results becomes unreliable for higher degree polynomial because of round of error. So for the higher degree polynomial, the two things are there, it is computationally very costly, and also the results becomes unreliable because of the round of error. So to get rid of this one, these issues we apply for splines. So that we will discuss in the coming lecture. So we will stop today. So today we have discussed the examples based on the Lagrangian interpolating polynomial and the Newton divided difference interpolating polynomial, and we have seen that whatever the method we are going to apply, we are going to get the unique interpolating polynomial. And then for the larger number of data, we are going to get the higher order polynomial. So to get rid of this one, we are going to start with the piecewise approximation, and that is we are going to discuss in the coming lectures, that is called the splines. So I hope you have enjoyed this one. So thanks for watching this, thanks very much.